Hello everybody, I'm greeting you all on this marvelous weather. It's springtime here in Munich. Everything looks absolutely gorgeous. The sun is shining, the birds are singing, the nature seems to be celebrating and having fun. And overall, the whole environment is very much encouraging for staying indoors and thinking about mathematics and biology. I'm Alex Surnov, your host. Welcome to the YouTube channel Numbers, Life and More, and to the series of lectures dedicated to mathematics and biology. This is the second part of the lecture 4, titled Differential Equations. That's the final part of the lecture 4. And today we are going to talk about the qualitative theory of differential equations. Qualitative theory. So the main take-home message from the previous talk, from the part 1 of the lecture 4, was that multiple differential equations often don't have solutions expressible in elementary functions. Even though they do have some solutions, none of them can be represented as a combination of pluses, minuses, exponents, sine functions, and so on. But nonetheless, even though such a situation is very abundant and very prevalent, the researchers do need to know how to analyze these equations and how to make some statements about their solutions. As shown here in this slide, I'm just reminding you that in the previous lecture we discussed briefly, very briefly, we discussed the 80 equation whose solution is not expressible in elementary functions. We also faced the equations that describe chemical kinetics in the simplest possible bimolecular reaction when the compounds A and the compounds B react together and produce the compound C. And again, this equation doesn't have a closed solution in elementary functions. More so, there is often appearing a situation when we don't quite know the exact appearance of the differential equation. So, for example, our biological intuition dictates us that a certain variable x evolves as time passes, the time is t, being governed by this equation, dx over dt equals to certain f of x, but we don't know f of x precisely, either because we lack a strong biomathematical theory that truly describes this process, or because the process is very heterogeneous and in different individual cases it takes slightly different form. So assume that we know, all we know is the general shape of the function f of x. So for example, like this. For example, we know that the function f has the following shape when being plotted in the coordinates f versus x. What can we say in this case? Can we have some meaningful conclusions about the equations which we lack some information about, or which we in principle cannot solve in an explicit form? And the answer is yes. We can analyze them qualitatively. And here is the first example. It's an example of the qualitative study of a first order, one-dimensional ordinary differential equation written here. Let's examine how this right-hand part of the equation behaves. So we see that it doesn't depend on t explicitly. It depends on t only indirectly via the dependence on x. So we can plot the right-hand part of the equation entirely with no loss of information, just as a function f of x. We notice that this function vanishes in 3 points. And what does it exactly mean? This means that the derivative of x with respect to t vanishes when x takes these values. It means, in turn, that once we set the variable x in this position, either in x1 or in x2 or in x3, it will not change in time. It will stay constant as dictated by the fact that its derivative with respect to time is 0. Okay, we can start representing the kinetics of x with respect to time using this observation. We draw another chart. We introduce the time coordinates and the x coordinate, and we plot the x levels of x1, x2, and x3 as shown here. So far, we can make only one conclusion, namely that if x is placed exactly at each of these points, it will stay constant. Let's now give a certain increment to x. Let's see how it evolves when it's originally positioned elsewhere, not in those stationary states. Assume we put the initial value of x to the left of x1. What we notice is that the value of the derivative of x with respect to t is negative, because the derivative of x with respect to t is this function. So in this situation, the derivative is negative, so x is gonna decrease in time with no limit. And this is the part of the qualitative study of this equation. We gave a negative increment to x like downwards from the x1 value, and by seeing the sign, the fact whether the derivative is positive or negative, the derivative with respect to time, we conclude that x is gonna be decreasing. What would happen if we position the original value of x here? Here, the function f of x, which is the derivative of x with respect to time, is positive, and therefore x is going to increase. But it has no room to increase unlimitedly. It necessarily will be bounded at least by another stationary points of this equation. And then we have to conclude that when the initial condition of x is positioned between x1 and x2, the variable will be increasing and will be approaching a certain limit, and in this case the limit is going to be just x2. Similarly, we can continue this analysis and place the original position of x between the x2 and the x3 values. Again, the derivative of x with respect to time is negative here, and x is going to be decreasing, but it has now the lower boundary. It's bounded from below by the value x2. And it's going to be the limits of x when time is progressing. And finally, when we position the original value just above the x3, it will grow all the way to infinity, because the derivative with respect to time is positive, as shown here, and because there is no upper limit to this kinetics. So here is the summary. We have 3 stationary points. we see the sign of the derivative of x when we position the original original state of x elsewhere beyond these points or between them. And we conclude that x1 and x3 are unstable stationary points. The kinetics deviates from them when a minor increment is given, as here the kinetics deviates from x1 and the kinetics deviates from x3. But x2 is a stable stationary point. The kinetics converges back to it once a small increment is given. Well, the increment must be small in such a way that the original value of x doesn't cross the boundary between the attraction areas of different stationary states. If the original value of x is still within the segments between the x1 and x3, then the kinetics will be converging to x2, which is sitting between them. And this observation gives us, actually, it can be generalized. It gives us an important hint, an important feature of the equations of these kinds that we can study, namely that if the right-hand part of the equation being plotted like here is increasing in the stationary points, like here it is increasing in the points x1 and it is increasing in the points x3, then the corresponding stationary points is going to be unstable. However, if it is decreasing in a certain stationary point, this stationary point is going to be stable. Okay, so, and a good illustration of it, a good example, is the equation of limited growth or bounded growth, whatever way I called it in the last lecture. That's the Fairhurst equation. The Fairhurst equation that describes the kinetics of a certain population of proliferating objects. It may be cells, it may be some animals, it may be microorganisms, of which originally is very similar to the simple exponential growth, dx over dt equals to rx, where r is constant. However, once x grows, the other term of this equation becomes dominant, namely the competition term, which induces the kinetics to be bounded and to approach a certain limit when the population becomes very dense. And here we use just, well, in the previous lecture we solved this equation explicitly, so we know its behavior. But also we can study it qualitatively, as we just described. So here is the general look of the right-hand parts of the equation. Here is x, the horizontal axis is x, the vertical axis is f, meaning the right-hand part of the equation. And here is an unstable stationary point in 0. Here is a stable stationary point to which the kinetics converges. And here is how the kinetics looks. Obviously, I drew it by hand. It's not an actual graph of the solution, but, well, it's pretty descriptive. Okay, cool. That was an introduction to the qualitative theory of differential equations. At least you understand now the logic. You understand what we are going to do. We're going to be studying the equations in the current lecture without actually solving them. We'll try to infer some patterns, some behavior, which are dictated by global properties of the equation's right-hand part, of the equation in general. The next topic, which is very important and which is quite coherent to the stability analysis that we just did right now, is linearization of nonlinear equations and the stability analysis through linearization. Let me remind you briefly some material from the lecture 2. In the lecture 2, in the lecture where we talked about just calculus, we introduced the concept of Taylor expansion. If we have a certain function at a given point of this function where we know its value, we can approximate this function, generally speaking, maybe not in some bizarre cases, but generally speaking, we can approximate this function in a certain neighborhood of the points of reference using various polynomials, the polynomials of various degree. You can, or we can, approximate the blue function here, which is logarithm of x in this case, using just the linear tangent line. We can approximate it better using a parabolic, quadratic tangent line, or a cubic tangent line, namely the tangent line of the order 3, 4, 5, and so on. The approximation will not necessarily be valid outside a certain neighborhoods of the points of reference, but within this region, within this neighborhood, it's gonna hold. And the linearization is a particular case of this operation where we are satisfied just with the linear approximation. When we don't care about the second or the third order polynomials, we just approximate the original function using the linear one, and we consider that this approximation is good enough for our purposes. Here I approximated a one-dimensional function, the function that depends on just one variable, but a similar procedure can be applied to functions of multiple variables as well. Okay, so once this is said, let's see how we can use this concept for studying differential equations. Assume we have this system of two equations. It has two unknown functions, the x1 and x2. They are both functions of t, and the right-hand side of the equation is dictated or specified, is represented by the two nonlinear functions, the p1 of x1 and x2 and the p2 of the x1 and x2. What can we say up front about this equation? We can try to find its stationary state by equalizing the right-hand part to 0. We remember that each of the functions, the p1 and the p2, is nothing more than just the time derivative of the corresponding variable, as shown here explicitly. So if we require the condition that both the p1 and the p2 are simultaneously equal to 0, it means that the functions x1 and x2 will not evolve in time when being set in the state that satisfies this algebraic equation, p1 equals 0, p2 equals 0, as shown here. So the condition p1 equals 0, p2 equals 0 implies that the solution to this equation, the x1 bar and the x2 bar, is a stationary point. So these are the particular points that satisfy this equation with the particular values of the variables x1 and x2. And in these points, if the system is positioned in this point, in this state, it's going to be a stationary state. It's not going to evolve. Now, let's linearize the functions p1 and p2 in the neighborhoods of these stationary points. Well, the writing is a little bit lengthy, but in principle it is just the same what we saw a couple slides ago when we linearized the logarithm function. So the first equation appears to have now the value of the p1 in the stationary point itself. That's the constant number. It's not a function anymore. It's just the value of the function p1 in the particular points x1 bar, x2 bar. Also, it has the derivative of the function p1 evaluated in the same point, x1 bar, x2 bar, times the increments of x with respect to the stationary point, x1. Okay, I apologize if you hear this ugly noise, but some of my neighbors just decided to drill something. Well, I will try to speak louder. I hope you will understand. I'm not going to give up. I'm not going to finish the presentation because of a neighbor with a drill. So, yeah, this is a linear term. So now this first equation becomes a linear combination of the x1 and x2 with a certain constant coefficients, namely the derivatives of this equation, and some other terms. So this all little notation is nothing else than just all the other terms of the Taylor's expansion that we consolidated together. Essentially, the all little notation means all terms or any term which vanishes faster than this difference when the difference tends to zero. If you want to learn more about it, just read the book by Courant and John, or read this Wikipedia article, the Big O notation. So here are the all terms that we assume to ignore. What we're curious about are just the linear terms of the functions p1 and p2. And here is the expansion done equivalently for the second equation. Now, well, what did we do? We approximated the original equation with the linear equation in the neighborhood of the identified stationary point. And we can study the linear equation's behavior using the tools that we discussed in the previous lecture, in the lecture 4, part 1. We have already solved an arbitrary two-dimensional ordinary system of differential equations, and we learned that it can be either exponentially converging or exponentially diverging from or to the stationary points. And also, alternatively, it can be converging or diverging by a spiral, by spiraling around the stationary points. And assume, well, we don't know what these functions are. We don't know the values of the derivatives, but assume, just for the sake of visual beauty, that the linearized system converges by spiraling towards the origin, towards the points where these differences vanish. So the x1 equals to x1 bar and the x2 equals to x2 bar. Good. So for this case, there is a theorem which you can see, for example, in the following Wikipedia article, or in some books that I recommended previously. So see here stability analysis and Hartman-Grobman theorem. So the theorem is that if the solution of the linearized equation is non-degenerate, if it's surely converging or diverging, then the original system bears the same behavior in at least a small neighborhood of its stationary points. The same qualitative behavior. So the bottom chart shows how the linearized system behaves. It's just a spiral like this. And the original system spirals as well, but the spiral itself may be a little bit distorted. So you see some flattening, a little bit flat regions here and some bumps to the left here, but the general pattern is the same. Okay, so that's the take-home message. You can study the behavior of a system in the neighborhoods of its stationary points by analyzing the linearized equations using the tools from the previous lecture. You can simplify the original nonlinear set of equations by linearization. Okay, good. So here are some examples coming shortly. Some examples. The so-called Lotka-Volterra equations. That's the equations that are usually interpreted as the kinetics of two populations of organisms, the predator and its prey. And let's have a look. Who is the predator? Who is the prey? So X multiplies freely according to this term, and also it experiences some decrease due to the interaction with Y. So X is the prey. Without Y, if Y is 0, it just grows exponentially. However, if there is Y, then the interaction between X and Y, the encounterment between X and Y leads to the decrease of X. So, okay, X can be hares and Y can be wolves. And in the absence of hares, wolves just die of starvation. Their population vanishes exponentially. And in the presence of hare, in the presence of hares, in the presence of the hare population, the wolf population gets the positive increments to its velocity. It starts growing. Good. So we have two stationary solutions. We can infer it by solving the equations a times x minus b times xy equals 0 and negative c times y plus d times x times y equals to 0. There are two stationary solutions, the origin and this points, C over D, A over B. And we can linearize this equation, the original equation, around a certain stationary points, which I generally denoted here as x bar, y bar. And let's examine the behavior of this situation around each of the stationary points that we just identified. In the first stationary point, the kinetics becomes decoupled. X diverges like exponentially from the stationary point, and y converges to the stationary point. So one way or another, the equation of this kind tells us that the overall kinetics, x and y, is not converging back to the state 0 and 0. X seems to be increasing, y seems to be decreasing in the neighborhood of this point locally. I'm not saying about the behavior of these variables in infinity, but locally, a small increment given to x and y from the stationary point 0, 0 leads to the divergence of the system from this point. Okay. What happens when we use the second stationary point in this equation, when we substitute the C over D instead of the X bar and the A over B instead of the Y bar? Well, some arithmetic needs to be performed. What do we see? Well, we just substituted these two guys instead of Y bar and X bar. And we see that B's are cancelling each other here, and D's are cancelling each other. And after a certain simplification, after like cancelling all these terms, we introduce first of all another set of variables. We shift the stationary points to the origin. So instead of examining x and y, we examine r, which is nothing else than just x minus the x coordinate of the stationary points, and s, which is also nothing else than just y minus the y coordinates of the stationary points. And in these coordinates, the system simplifies tremendously, but it's not longer decoupled as in this case. So r depends solely on s, and s depends solely on r. And then, having analyzed this system using the tools from the lecture 4 part 1, we can conclude that the behavior is degenerate. It's neither converging nor diverging towards or from the original stationary point, but it rather circles around it, like this. So you give a small increment from the stationary point, the system starts circling around it and keeps circling all the time, periodically. You give another increment, a larger or smaller one, or the larger one in this case. The system just starts circling with a greater magnitude. And it's not converging, neither it's diverging. In this case, generally speaking, the theorem that we discussed previously doesn't say much. The behavior of the original nonlinear system may recapitulate the same pattern, or some higher order terms in the Taylor expansion may dominate, and the kinetics changes. It may not be the same as the kinetics of the linearized system. However, particularly in case of the Lotka-Volterra system, one can prove that the behavior of the nonlinear system is the same or has the same pattern as the behavior of the linearized system. Namely, it does orbit around the stationary points in closed loops. Okay, that's just one of the cases, one of the examples. Another example is the two-dimensional competition equations. We already have discussed the one-dimensional competition equation when the population grows exponentially first, and then it reaches some limits because the population becomes too dense. What happens if we have two populations of the same kind? We have here the population X and the population Y, and they both have this exponential growth term, but they both experience the effect of competition. Their growth rate vanishes as X and Y grow, and the impact of this competition is different in different populations. That's a crucial thing. The system is not degenerate. It has stationary points that is independent from the origin, where you placed the original values of X and Y, and we can study it. If B would be equal to, if B was equal to E and C was equal to F, then the system would be degenerate, and the kinetics would be more complicated. We may return to such an example at some point later, but not in the current lecture. But if these numbers are different, so if the impact of competition from X is different on X and on Y, and mutually if the impact of competition from Y is different to X and to Y, then we can study the system just the same with the same tools which we already discussed. Again, we have two stationary points, 0, 0, and this point. We again shift the origin to the stationary points that we identified. We introduce the coordinates R and S. We linearize the system, and we see that the solution converges to the stationary point. So here I plotted R and S with respect to t, just because if I plotted X and Y, the scale would be off. They will be converging to the stationary states that are too remote from each other, and it would be difficult to fit on the same chart. But the qualitative behavior of X and Y can be seen from this plot of R and S as well. So the variable X converges more or less exponentially to its stationary state, shown here, and the variable Y converges exponentially to its stationary state. As we deduced from studying the linearized system using the tools of the analysis of the second order ordinary differential systems in the previous lecture. Okay, great. So congratulations. The stability analysis is more or less covered. We did discuss the main parts of it. Of course, if you want to learn it deeper, please go to corresponding books. If you just need this material simply for, discussing your results and your approaches with your bioinformatics colleagues, then this knowledge must be pretty sufficient. What we wanted to discuss next, actually, we wanted to discuss next a whole lot of different things. We wanted to discuss next the whole galaxy. It's such a beautiful theory with such a beautiful science with so many peculiar results. But to stay concise, let's discuss the three major topics. First of all, let's see how we can identify or how we can study the long-term behavior of systems that have unstable stationary points. So if the system diverges from the stationary points, then what? Also, we will discuss how this behavior can change. In the current example and in the previous example, we already saw that there are two stationary points and there is an individual pattern of behavior around each of them. The system converges towards the second one and it is diverging from the first one. So at which points the behavior changes. And also we will return back to the results of Andrei Tikhonov, whom I mentioned in the previous lecture, and whom I told about that we will really encounter his name once again. And we will discuss a smart way how he proposed to simplify a complicated set of equations in order to say more about them. Okay, so in light of this, the next topic is going to be bifurcations and limit cycles. It's going to be quick. It's going to be just one slide. Bifurcations. So assume there is a system that has a stationary point somewhere here, somewhere slightly above 3. Well, maybe it's pi. I think I made it pi when I wrote this equation. So it converges from both sides. So no matter where you place the initial point, the kinetics will move the variable x to the stationary point. If a certain parameter a, which is included in the original differential equation, is smaller than a asterisk, where a asterisk is just a fixed number. So the dependence of the right-hand part of the equation on a is such, we made it such, that once a is smaller than a asterisk, the kinetics is converging. But then something happens. Then once the parameter crosses the value of a asterisk, the stationary point stops being stable any longer, and the kinetics diverges from it and accumulates around two other stationary points. So this picture does not contradict to the theorem that requires what's the name to it? The continuous dependence of the solution of the equation on the parameters, because that theorem works in a small domain, in a small neighborhood of the initial point. So when A is very close to A asterisk, regardless whether it's smaller or larger, the initial behavior of the equation in a close proximity of 0 will be very similar, regardless whether A is larger than A asterisk or smaller than A asterisk. But beyond that small region here, yes, the long-term behavior does become different, and the original theorem doesn't state anything about it. So such a phenomenon is called a bifurcation, when the stationary point either disappears, or when it loses stability, or when it gains stability, or when it splits in two stationary points. So this all is called bifurcation. An interesting example of bifurcations is when originally there was a stable point with a spiraling kinetics originally, and then it loses stability, but instead it generates a stationary orbit towards which the kinetics approaches asymptotically. And that's called Hopf bifurcation. Well, actually, by the way, I want to make a disclaimer. I really don't want to seem like a person who does nothing but referring to Wikipedia articles. Those Wikipedia articles I'm referring to simply because they are indeed pretty good. And they do contain a lot of valuable information, and they are understandable, and they are quite easy to read. Just remember, I'm not here simply to interpret Wikipedia or refer to it. In case if I can't find an appropriate illustration to my material in Wikipedia, I recommend other books. And by the way, this Kaplan and Glass book is, I highly recommend it. Please go to it, go look through it, go check specifically those figures and the corresponding text. It's written for natural scientists, it's written for biologists, I guess, and it describes all this material maybe in more details, but also simply. So yeah, I will give a full bibliographic information later in the end of the presentation. There is going to be a separate slide for that. Okay, so there was, returning back to Hopf bifurcation. Assume there was a stationary stable point towards which the kinetics was approaching by spiraling around it, and then something happens, then the constant parameter changed, and this point lost its stability, but instead this limit cycle appeared. And the kinetics of the system now looks just like this. It's the oscillations of the constant frequency, but its amplitude asymptotically approaches the radius of the circle that appeared. And there is a method to study whether the system has such a cycle or not. This is called the Linearization method or Linearization equation. Again, referring to this article simply because I'm doubting that biologists need to know such a technical tool. By the way, if you do think you need to know it, leave a comment and ask me to highlight this method specifically in further lectures. It would be actually beneficial to obtain some feedback from you. Okay, so we're done with bifurcations and limit cycles. Let's now go to the Tikhonov's theorem. Okay, yeah, let me have a sip of my tea. Tikhonov, he was a great mathematician, and he was a great applied mathematician. He actually focused largely on the methods to solve or to study the systems that cannot be really solved explicitly, but which are needed to be solved for some practical purposes, for some practical some practical goals. You know, if you're an engineer in an industry and your boss comes to you saying, "Look, we have to compute how this process behaves because otherwise we're gonna spend unreasonable amounts of money on experiments, and I don't care that there is no an explicit solution. You're a smart guy, we're paying you for being smart, so just shut up and think up something productively." Then you're faced with this practical necessity. You have to invent an approximate method of solution or approximate method of studying. You just have to deal with this practical problem. And Tikhonov was extremely good at it. Now, eventually coming to his theorem. Assume we have a system of a system of two equations. dg over dt equals to a certain function p of g and e, and de over dt equals to q of g and e. And assuming a grotesquely a grotesque example, assuming an outrageous example, when one variable here is extremely fast and another one naturally is extremely slow. For example, g is the amounts of grass in a savanna, and e is the size of the elephant population that feed on this grass. Obviously, grass grows very fast and elephants multiply very slowly. And by the way, I am a biologist. I know if some of you just say that grass is not the exclusive food for elephants, I know that elephants don't feed on grass exclusively. I know that they consume many other herbs and plants and stuff. But for the sake of brevity, let's just, call any vegetation suitable for elephants as food just as grass. It will simplify the discussion. So, okay, so there are elephants and there is grass. Let's examine the behavior of this situation at a small time scale. Oh, and actually, by the way, here is the reference to the original publication of Tikhonov. Again, the full bibliographic information will be given in the end of the presentation. So assume that time passes just from 0 to 1 week. We don't look so far beyond this period. If time passes from 0 to 1 week, then we can assume that the population of elephants just doesn't change much, that the value of E of t is approximately constant, and it's equal to E of 0, because elephants multiply very slowly. Well, I don't know, how many baby elephants are you expecting to be born within 1 week, within an arbitrary week? Probably 0 or 1 at most. But the herd of elephants is more or less steady in this short time. But the grass evolves rapidly, because the elephants just came to the savannah full of grass, and during this week they ate as much as they could, and the value of G decreased and stabilized at a certain level. So the elephants, which are marked in red or orange here, they stay the same, but the grass dropped and stabilized. That's a key thing. It dropped and then stabilized. What is the stationary state of grass in this situation when we assume the elephants to be constant? The stationary state is a certain function of the number of elephants. Might there be more elephants originally? The stationary state of grass would be lower. Might there be a bit fewer animals, fewer elephants? The grass would drop less significantly, magnitude-wise. So the stationary state of the grass at the time frame of 1 week depends on the number of elephants. Now let's extend our time frame. We take this whole segment, we shrink it. I mean, we just extend our attention beyond this period. And we see that soon the population of elephants starts growing slowly. So here maybe 1 baby elephant was born. And the grass dropped again a little bit, because the elephant's population changed. But again, it changes very slowly. It stays steady most of the time. The grass dropped almost instantaneously and again stabilized at a new stationary state. At a stationary state that is dependent on the new value of E, on the new population of elephants. Then another baby elephant was born. The grass almost instantaneously dropped again and again stabilized. Then 1 elephant died or migrated out from the population. The grass a little bit replenished, not entirely, not to the full original state, but a little bit replenished, and so on. The elephants kept multiplying, the grass started following them, and at each step of elephant's multiplication, the grass abates this kinetics almost instantaneously with a very small lag and stabilized quickly. So here it is highlighted in yellow. If time passes from, let's say, 1 week to 10 years, then we can ignore the kinetics of the grass, the differential kinetics of the grass. We can assume that at each given time point, the grass state is its stationary state dictated by the population of the elephants at the given time point. So this G bar is the stationary state that the grass takes if the population of the elephants is not changing. And we can express it as g bar equals to a certain function f of e of t. And here, again, just the same graph as before, but a little bit expanded, a little bit magnified. So at the given point t, the number of elephants is equal to this level, to this dashed pink line, and the level of grass is fully determined by this dashed pink line, by this level. And it's exactly the f of e of t. This happens specifically because the kinetics of grass is very fast, because it almost instantaneously stabilizes itself on the quasi-stationary level. Now we recall that our equations are not discrete, they are differential, they operate smooth continuous functions. We assume that the elephant's population grows not in discrete steps, but somehow, well, you know, somehow continuously. And essentially what Tikhonov's theorem claims is that the solution of this equation, the equation that describes the elephant's population, regardless of the differential kinetics of the grass, is very similar to the exact solution of the original system. So we essentially can simplify the original system by ignoring the differential kinetics of the grass itself and by placing the quasi-stationary state of the grass instead of the grass variable in the second equation, as shown here. And we can be solving only the one-dimensional equation, which is always simpler than solving a two-dimensional equation. How can we represent it graphically? Let's erase the AI-generated images. So here is a two-dimensional plot, and the population of elephants is on the horizontal axis, and the quasi-stationary kinetics of grass is depicted as this bold green line. And so essentially it means that if the population of elephants is here, if the number of elephants equals to this level of E, then the stationary number of, or the stationary amounts of grass in the savanna is going to be just like this, So this amounts of grass corresponds to this amounts of elephants if the elephants are assumed constant, if they are not multiplying. And how our kinetics works in practice? Well, we start in a certain level, depicted by this point, when we have very few elephants and a lot of grass. Then the grass amounts quickly approaches this quasi-stationary kinetics. The elephants quickly eat all the grass they can given their original population size. And after that, the exact solution of the original equation, represented here by this violet thinner line, will follow the quasi-stationary kinetics dictated by the function f of e. And finally, as a summary, here is the same thing written in letters. If time passes from 0 to 1 week, then we can assume the population of the elephants constant. G evolves from G0 to its equilibrium G bar equals to f of e of 0. If we examine a much larger time scale, then we can assume that G remains in its equilibrium, which depends on the elephant's population at each given time point, like this. And this trick, proposed by Tikhonov, allows us to decouple this original system of equations. We first solve the equation dg over dt equals p of g and e of 0 instead of e of t. And this equation depends solely on g. And this equation represents the relaxation periods, the periods of 1 week. And then we solve the equation for the elephants, which also depends only on G now, only on E now, only on its corresponding unknown function, because the grass is quasi-stationary, and this is called the quasi-stationary mode. So this is the relaxation mode of the system, and this is the the top equation is the quasi-stationary. The top equation is the relaxation modes of the original system, and the bottom equation is the quasi-stationary modes of the same system. Okay, great. Now we will examine two specific examples of how to use the Tikhonov theorem. And after that, we will talk a little bit about dynamical chaos, and that will be it for today. But yeah, we still have 3 topics to discuss. I will take a short break, and I will be here shortly. So here am I. I'm back. This is the first example of the 2 examples that I wanted to discuss. It relates to the model of how neurons fire, how neural cells generate the action potential. And first they invented the so-called Hodgkin-Huxley model, which is both kind of a model and just a general framework of how to think about modeling neurons. It couples the electrodynamical equations together with some pre-assumptions about nonlinearities appearing in the neural tissue. And based on this framework, for which, by the way, the authors received the Nobel Prize, the successors, the further generation of researchers developed a more formalized set of equations, which is called FitzHugh-Nagumo equation, or set of equations. And a particular case of this equation is the so-called van der Pol equation, or van der Pol oscillator, which originally was invented actually for describing certain electrical circuits, not quite neurons, but somewhere in technology. Nonetheless, it's a valuable biological model, and this is a good example of how the Tikhonov's theorem can be used for describing and for analyzing the stable cyclic behavior, similar to what we saw already previously in one of the slides today. So there are 2 variables, z and y, and why I'm calling them z and y and not x and y, it will become clearer in the section when I will talk about dynamical chaos. So for now, let's just take them as they are. And y, the kinetics of y is quite simple. It's just proportional to z. But the kinetics of z has this nonlinear term here, the cubic term. There are two parameters, constant parameters, a capital and epsilon, where epsilon is considered, well, they both are considered positive, but epsilon is considered small, like quite close to zero. I'm not gonna really discuss the technicalities here, but the fact that epsilon is expected to be small actually has a lot to do with the formulation of the Tikhonov's theorem as such. The limits in which we can consider Tikhonov's approximation relies on a certain parameter to be small. And more details about it you can find in Tikhonov's paper or in some textbooks on this. Honestly speaking, yeah, as I said, if you want me to discuss this deeper, just leave your comments and say, hey, we're not really satisfied with the degree of depth that you are providing. We're joining this channel to be informed more specifically about the details, and I will be happy to discuss it. But for the sake of shortness, in this course of lectures, in this particular lecture, I'm not going to discuss that really deeply. So, okay, let's start analyzing this equation. We first assume, based on the way how Tikhonov's theorem is structured, that z is going to be the fast variable. And if so, then it means that, hold on. If so, then we can write down this equation. It's purely analogical to the equation g bar equals to f of e of t in the previous example. So we're just computing the quasi-stationary state of z with respect to the given value of y, which we so far consider constant at this smaller time scale. Okay, so the quasi-stationary behavior, quasi-stationary state of z is described by this cubic curve here. And how does it behave? Well, its behavior depends on the value of y, the value of y that we select. If y is positive, the curve is shifted downwards. If y is negative, the curve is shifted upwards. If y is 0, it intersects the origin. And how to analyze the charts of functions I explained in the lecture 2. That the constant increment of function results in a shift of the function's chart just upwards or downwards. Okay, let's now study the kinetics of z at a smaller time scale while y is constant. We use the same tools that we already employed today in the beginning. Well, we split first these three cases actually in separate graphs. And then, just as before, we notice that there are two stable stationary points and one unstable stationary point. If the deviation of y from 0 is not super big, if it's not too negative or too great, like to the positive direction, if it's somewhere around 0, there are two stable stationary points and one unstable one. But if y becomes either too negative or too positive, the bifurcation happens, and one of the and like two stationary points kind of merge and disappear. Here just the rightmost remains, and here the leftmost one remains. Now, okay, so we understand that if y is constant, z can be placed somewhere, and then its behavior will be dictated by this curve and the stability of the corresponding roots. Return back to the entire system. We set the initial condition of y and z. Y is negative, but not too negative. It's slightly negative. Z is positive, but is located between the two roots of its quasi-stationary curve that we identified some slides ago. The curve is now flipped. It's sort of the inverse curve, although not specifically the inverse function, of course. It's yeah, just think about this as a function of as like y being the function of z, not z being the function of y. And I wrote it and I drew it here in such a way that it intersects the zero, the origin. So here is the original point, the initial point, sorry. According to what we learned about z in the previous slide, it will quickly move towards its quasi-stationary state, like here. And we see that y stays almost steady, almost constant, whereas z experienced a large increment in a short period of time. And after that, Tikhonov theorem, the Tikhonov theorem comes in play. Once z has reached its quasi-stationary state, we can substitute the equation for y with the corresponding equation where z is just dictated by the quasi-stationary curve, by this curve. This curve has a closed, what's called a closed solution in elementary functions, as I mentioned in the lecture 2, because it's the root of a cubic curve. But the formula is so bulky and so like complicated that I'm not writing it here. I will call it sporadically Cardano, the Cardano formula, or just I will call it the quasi-stationary curve of z in this case. Okay, so now we have another state of the system. Here, the y and the y variable and the z variable all came in agreement, and they start their further travel from this point. We remember that z is nothing more than just dy over dt, well, proportional to it, I should say. And we can again use the graphical tools of analysis of and simple one-dimensional ordinary differential equation to see how this system will evolve. So z, aka dy over dt, is positive, meaning that y is going to grow, and z itself, the variable z, will be following y along the quasi-stationary curve. And the system will slide along this curve like this, all the way until it suddenly comes to the point when this equation undergoes a bifurcation, when x becomes just too large and stationary point disappears. So when y becomes too large, this hump here sinks below the z-axis, and the stationary points just doesn't exist anymore. What does z do in this case? Z starts sliding quickly towards the only stationary point that remains, and this is the negative one. So once the system travels all the way until the end of this branch, it will fall down onto the next stable branch, and everything will repeat. The system will again settle here in a quasi-stationary state and slide slowly again along this branch until it finds this critical point, and then will rise back, or it will leap on the next stationary branch, stable branch. And that's how it looks in the numeric simulation. We started from here. We quickly reached the quasi-stationary situation, and the system just oscillates in a loop around this circuit here, around this curve. Quite understandable, quite illustrative. And just this example emphasizes the importance of the Tikhonov's theorem and this slow/fast kinetics analysis for revealing unobvious, complicated behavior patterns. Okay, I took again a short break to close the blinds because the sun was shining just straight into my eyes and was sort of preventing me from seeing the slides. Look, there is one more example of how to use the Tikhonov's theorem applied to biology, and that's the so-called Michaelis-Menten equation, the equation of enzymatic kinetics. We consider the reaction where a substrate S gets converted to the product P with the help of the enzyme E. And the way how this reaction is actually happening involves the creation of a short-living complex C, which is the product of binding the substrate to the enzyme. Let me take the pointer. So here is the substrate, here is the product, here is the enzyme, and S and E just react together to make the complex C, which then degrades into the product and the enzyme again. And importantly, the reaction C to P plus E is shifted rightwards very much. The velocity constant K2 is much greater than the K sub -2. This equation, this kinetics, can be analyzed in the same framework as we just discussed, and an exhaustive description of it is done in this work, Newton and Volter, particularly in the section 3. So please refer to it. But the idea behind this analysis is the following. We write first the chemical kinetics equations for all these reactions like this, employing as well the conservation laws, so we don't have to really write differential equations for E and P because they are bound to other components of the system by just mass conservation. And when we substitute these expressions into these two top formulae, we get the system of two equations. And now, based on the fact that K2 is very large and K sub negative 2 is small, one can prove that the Tikhonov's parameter, the epsilon, is expressed in the following form as shown here in the bottom. And then the kinetics of C, the complex, can be also represented in a quasi-stationary way, like the kinetics of grass in the elephant example, like the kinetics of Z in the van der Pol example. And then the approximate equation that governs the kinetics of S in a quasi-stationary mode is the following as here. So it's a sort of rational function in the right hand part. So there is a linear function at the top, linear function in the bottom. Is just the ratio of two linear functions. Is it better now? Yeah. And it's of course quite easy to analyze. It's always easier to analyze a one-dimensional equation versus two-dimensional equations. Well, how does the system behave? When epsilon is large, when epsilon is small, when it's nearly zero, it's useful to depict the system in the coordinates negative derivative of S versus S. These are going to be our two variables. And then the quasi-stationary curve of the negative ds over dt is going to be this hyperbola, this ratio here. So the system gets started at some position, again drops on the quasi-stationary curve in a relaxation mode, and then starts sliding along it all the way until the reaction is fully completed, until all the substrate is converted. So the V here is the velocity, essentially just this negative ds over dt. Okay, fine. The derivation of this equation is a little bit more tedious than in the previous examples. And honestly speaking, it employs some other reasoning about this fast/slow kinetics, which I haven't touched. But nonetheless, the idea is just the same as I have described. The example is here, and I don't think you really need to worry much about technical details. If you want some technical details, go to the paper referred to in the previous slide. Now we have the last topic for today. It's dynamical chaos. And a little bit of history now. There was a researcher with the surname Lawrence who studied some air convection in the atmosphere. Essentially wanted to predict weather, if I'm not mistaken. And he computed the behavior of his differential equation. It was the set of three differential equations. He computed them numerically using just a machine, a computer. And then next day he decided to repeat his computation, and surprisingly he found that the very small increments in the initial data resulted in surprisingly large deviation of the behavior of the system in time. He found something like this. Not exactly, but something like this. So there are two trajectories of the same process with the unknown functions x, y, and z. And he started with a slightly different initial points at the order of magnitude, I don't know, like 0.01. And then for some time these functions behaved similarly in full agreement with the theorem of the continuous dependency of the solution of differential equations on the initial conditions. But then once they passed beyond the neighborhoods of the initial points in which the theorem holds, they started deviating from each other like crazy. And it's a strange behavior. We know how a system can be unstable in a point. It's just the good example to it is the exponential growth. All the trajectories are diverging from zero and keep growing exponentially. Okay, fine. That's the example of a system being unstable in a point. We know how a system can be even unstable in a point and being bounded. It's the example of the limit cycle. All the trajectories are spiraling away from the origin, and then all of them approach the same cyclic trajectory, the limit cycle. But here, Lorentz found something surprising. He found that all trajectories are unstable while being confined in the same compact domain of x, y, and z. They repel from each other, they never repeat, they never converge to any points or any stable trajectory, and they uniformly fill a certain domain, which appeared to be quite complicated actually, this domain. What is this? How can we imagine such a situation? And surprisingly, in order to imagine it qualitatively, in order to imagine an example of this behavior, we again will make use of the Van der Pol oscillator. Let's recall the Van der Pol oscillator that we just have discussed. So here is the equation. The red cubic curve is the quasi-stationary state of Z. The blue curve represents first the relaxation kinetics, and then it just wraps itself around the quasi-stationary curve in a loop like this. Here is the limit cycle. Let's introduce another coordinate to this system. We're not going to use it just yet, but we at least will look at the system in a three-dimensional picture. So here are the old z and y, and also we added the x coordinate, which just does nothing for now. And again, here is the relaxation phase, or relaxation mode. The blue line is just the slice of this green cubic surface, and here is the limit cycle. Now let's add to this picture two more dynamical systems. We're not going to couple them yet in the same set of equations. We just plot them together with the previous one. And those are going to be just linear systems with an unstable focus. And I remind you that an unstable focus is just the spiral that diverges from its center. which exponentially, diverges while looping around the center. So here is the general form of this linear system. The x bar and the y bar are nothing more than just the coordinates of the center of the focus, the x and y coordinates. And z is, as I already mentioned, what it is. It is the Cardano function of y, meaning the reverse function of the cubic polynomial. Well, one of the branches of this function, because the function is not uniquely unambiguous. Therefore, you can just compute the inverse function of it only in a certain domain, in a certain branch. But nonetheless, you all understand what I mean. We just plot these two more linear systems like they are plotted here. 1 and 2. Two spirals. And now we're gonna couple them together with the first limit cycle. And let's see what happens. What will happen if we join these two equations together, just simply by adding up the right-hand parts. We start from the initial points here. We quickly pass through the relaxation kinetics, and then the system experiences the effect of the focus, while Z is still being almost constant. The cubic or the Cardano function is not changing much here in this region. So the focus starts diverging so assume there were two original points very close to each other, two initial points. They both dropped onto the focus, and it started deviating them from each other because it spirals exponentially. And at some point, while spiraling, one of those points, one of those systems, passes beyond the instability points, the instability line here, and it drops onto another branch of the van der Pol oscillator. Whereas the other point, the other system, keeps spiraling for another couple of loops around the focus until it eventually gets on the other branch as well. The focus, therefore, introduces the deviation between the two systems that starts from very close original points, very close initial points. They both drop here, they get an exponentially increasing increments while spiraling, but they don't migrate to infinity because the van der Pol limit cycle always confines them in the neighborhood of itself, if you will. Once they all move somewhere further, they will necessarily leap onto another branch of the van der Pol oscillator, which will prevent them from going to infinity. And that's how it looks. So here is the initial point, spiraling, leaps upwards, keeps spiraling again, keeps accumulating the error in a way, right? Then drops back, but it never drops to the same trajectory that it already has gone through. It drops in a close proximity to it, but not, not exactly. Technically speaking, I made only one linear system here with one set of parameters, C and B. And I made the coordinates of the focus to depend on Z. So when Z is small, the coordinates of the focus are somewhere here in the positive domain of Y. When Z is positive, the coordinate of the focus shifts to the negative domain of Y. So instead of using two individual linear systems, I used one with a variable coordinates of the focus. But the idea is just the same. What can we say about this behavior? Well, it does deflect from each other two points, that's systems that start from neighboring points. That's number one. Number two is that it can be proven. I don't think I really can give you the reference right now, but it can be proven that such systems are composed of the infinite number of unstable limit cycles. So among these trajectories, there are some that are indeed closed. And if a point sits on them, it will just continue going around all the way to infinite, all the time. But these trajectories are unstable, and even a minor deviation from them will result the points to shift, not to stay in this closed trajectory anymore. And there is the infinite number of these trajectories in the system. And the collection of these trajectories indeed form what is called the strange attractor, or a fractal attractor. Such a domain in this three-dimensional space in which the system gets trapped, although being unstable. Why it is called fractal? Because if you carefully assess the dimensionality of the whole collection of those of this infinite number of the closed trajectories, this dimensionality surprisingly is going to be not integer. Previously, we studied only integer dimensional spaces, and the definition of dimensionality was actually what is called the number of linearly independent vectors, the maximal number of linearly independent vectors in the space. In the two-dimensional space, there are at most two vectors that cannot be, cannot be represented as a linear combination of each other. In the three-dimensional space, there is three such vectors, and no matter how hard you try, you can't represent the four. I mean, every other vector will be represented as the weighted sum of the three original vectors, and so on. So the dimensionality is just this: is how many independent coordinates you have in a space. 3, 2, or just one in case of a straight line or a curved line. But some spaces, some strange objects, have non-integer dimensionality, which is defined differently, which is defined as a rate of the size of coverage of these objects. So if you cover these objects with little balls and you tend the size of each ball to 0, how many balls do you need to cover this object? Well, if you cover the line with those rings or balls, their number will scale linearly as the first power of the size of the number of the balls. If you try to tile a plane with balls, they will scale quadratically. You will have to tile them in both directions, and yeah, it's going to be x times x. If you try to fill a space with some closed, you know, balls or whatever, they will scale as the third power. But some spaces have this weird property that the coverage of some template tiles will scale with a non-integer power, with a non-integer exponent. And those objects are called fractals. These attractors, these strange attractors, belong to fractals and share their properties. And that's probably it. What I want. No, it's not it. The message, the take-home message from this is that be aware of the instabilities that can happen in the non-linear systems. That's the crucial thing. That's I want you to memorize before the lecture is over. I understand that you might be quite exhausted already, but remember, look, if someone comes to you and says, I just generated a very powerful differential equation that can model your experimental data, all your complicated dependencies between your variables, regardless what you're studying there. You may be studying cell populations, you may be studying animals, you may be studying some biochemical reactions within the cell. So there are many components to these systems usually, and someone comes to you and says, look, I wrote a complicated equation that covers all the dependencies. And then what you should be particularly aware of is that with a certain combination of parameter values, such a system may exhibit this nasty behavior, this instability, when a little increment to the parameters or to the initial condition will result in an absolutely wild digression and the deviation of the trajectories inferred. So just keep this in mind. Many bioinformaticians also underestimate and under-respect the importance of this effect, and you should not. And therefore I am telling you about this. And if you listen to these lectures carefully, you will know how to avoid these hidden obstacles, or at least you will be aware of them. What other attractors can differential system have? Well, they can have a point as an attractor. That's the simplest thing. We learned multiple systems that converge to a single point. They can have a closed trajectory, a limit cycle as an attractor, as the trajectory towards which everything converges. They can have strange attractors, and they can have an attractor that forms a torus. If there are two limit cycles, for example, if it's a multidimensional system and there are two limit cycles in different coordinate, in different like planes, in different coordinates of this system, then the system can follow the torus, right? It can form oscillation in one direction and a separate oscillation in an orthogonal direction, which induces the trajectory to like wrap around a donut or whatever. Okay, that's it. That's really it. That's what I wanted to say about differential equations. Thank you for listening. Sorry for being a little bit mumbling closer to the end of the lecture, but it's actually difficult to phrase everything. On this, please don't forget to like the video, to subscribe. wait for the updates and for next videos, and the next slide is going to have just the literature list. Goodbye, guys.